In this video, I'm going to introduce limits. I'm going to describe what they are. I'm going to do it two ways. I'm going to describe it informally, give you an intuitive way to think about it, and then I'm going to give you the rigorous, precise definition of a limit. Okay? Let me warn you right now that when you see the precise definition, it's going to look a little bit odd, and you're going to wonder why we have to do it that way. Okay, in future advanced calculus classes, you can study limits more, and you'll see why the rigorous definition has to be done that way. But in a first year class, we don't really have time or the desire to go into too much of those details, simply for because of the fact that we have a limited amount of time. All right. So let's first give the informal definition of limits. Okay, and I'm not claiming that this is rigorous, precise, and that it takes care of any confusion. Okay, but this will get us started. What a function value approaches as what a function value approaches as the input value approaches something. All right, so let me tell you what I mean by that. So we'll work on with this one for a little bit. So suppose that I had f of x was equal to x squared. So I want to know what happens as x approaches 3. Okay, the way that that's usually written is x with an arrow, so it's getting closer and closer to 3. So if I wanted to see what was happening to f, I could maybe see what is the value of 2.7, what is the value of 2.8, what is the value of 2.9, what is the value of 2.99? What is the value of 2.999? And you can, in fact, I encourage you, go ahead and write these numbers down. You find them with a calculator, and you will see that the numbers get closer and closer to 3. Excuse me, closer and closer to 9. So as you move down the list, it gets closer to 9. So f of 2.999 is probably 8.99 something. All right. So, and then 2.7 is something close to 9, but not as close as 8.99. All right. I don't know what the exact decimals are, but you can see for yourself with a calculator if you want. All right. So as the input gets closer to 3, then the function value gets closer to 9, so we say that the limit as x approaches 3 is 9. All right. Now, because we're going to be talking about limits, and we don't want to just always use words, and we want a uniform way to describe the limit we're thinking about. Here's the standard notation. Let me do it in red. So we say the limit as x approaches 3 of f of x, okay, and in this case that means the limit as x approaches 3 of x squared, and we're saying that that's equal to 9. All right, so there you have it. I've introduced the conventional notation for limits, and I've calculated a limit, or I've shown you how to calculate it, and then I've told you an answer. All right. Before I go on and add more to this, let's do a couple of examples. So the limit as x approaches 0 of the sine of 2x. All right. So you can plug in smaller and smaller values of x, and you will see that if you make a list, like this would be a table you could do. You could put x and then the value of the sine of 2x, and you could maybe do 0.3, 0.2, 0.1, 0.05, etc., etc. and then study the values as on the right side as you go down the list. Okay, if you did that, and by the way, you can also approach 0 from both sides, can't you? So in this column, I've approached it from, I've started with 0.3 and I've gone down from there. You could also do this. You could maybe start from negative 0.3 and go up from there. That's another way to approach 0, right? Okay, and then so you list the values and you look down and you say, okay, what is it getting closer and closer to? If you did that, you would see that the value is always getting close. The sign, the right side of each of those tables is getting smaller and smaller, and so it's if you kept getting close, if x kept getting closer and closer to 0, the sign, the function would get closer and closer to 0 as well. So the limit is 0. All right. Let me give you a few more, and you do these on your own. All right, find both of these limits with some tables. All right, so if you work them out, you would see that the second limit, as x gets closer to 4, the function 1 over x is getting closer to 1/4. And then the last one, as x gets closer and closer to 1, the function is getting closer and closer to 5. Okay, now I can guess what you're probably thinking. You're probably thinking, why do we have to creep towards the destination? Why don't we just plug in the what x is getting close to? So on the first one, why don't we just take the sine of 2 times 0? On the second one, why don't we just replace x with 4? On the last one, why don't we just do 5 times 1 cubed? Can't we just do limits that way? Doesn't this seem like a lot of effort for nothing? Okay, well, there's a reason that we have to do it this way. Watch this. Let me give you a different limit now. The limit as x approaches 0 of the rational function sine of x over x. All right, so let's do that one. Now, go ahead and try to simply plug in 0 like you may have been thinking in your head before. Go ahead and see what happens. What happens when you take the sine of 0 over 0? Okay, now if you do that, you will, if you just plug in 0, you're going to get 0 over 0, aren't you? So that is why we are not allowed always. Sometimes you can, but you can't always just plug in the destination and everything's fine. Okay, so this is your first example where you need to do it the long-winded way that I initially showed you. Okay, now you can see that it wasn't without reason. So now let's do it let's do this the proper way, the way I started describing limits. So with your calculator, maybe go ahead and plug in 0.1, 0.01, and 0.001, and let's do it in radians, by the way. All right, and then you could do more if you like, but that's enough to get us started, and then I will do that also. So the first one with my calculator, I get 0.017. Actually, I made the mistake of being in degrees. Let me switch to radians. Okay, so the sine of 0.1 divided by 0.1 gives 0.99. All right, now let's go back and do 0.01 divided by 0.1, and that gives 0.9999. And I'll do one more, sine of 0.001 divided by 0.001, and that gives 0.9999999. Now, the pattern that I notice, and you probably notice, is that the number of nines increases as x gets smaller and smaller. If you did it from the negative side, you would get the same thing. You would still get it approaching, getting on the sine value would still be approaching 1, okay? Because it approaches 1 from both directions, we say that the limit is 1, okay? So this is an important example, okay? Notice you couldn't just plug in the destination. You literally had to approach it, okay? There's lots of weird functions in the world, and a lot of them we have to take limits by creeping towards a certain value, okay? So let's go back to what I started with, and now maybe you can appreciate why, you can start to see why we did things the way we did. So it's what a function value approaches as the input value approaches something. Now, let me make something clear. We never actually, officially, you're not allowed to plug in the destination. So like if x is approaching 5, when you take the limit, you don't really care even what happens at f of 5. Okay? Now I literally, it literally doesn't matter. Okay? In fact, the value there could actually make things worse. It could confuse you. Let me show you what I mean by that. So let's say you had this function. Let's say that you had f of x is equal to sine of x over x, and then it's equal to, and that's equal to that for x does not equal 0, and it's equal to 2 for x equal 0. Okay, so now notice that this is just like the function that we just found the limit for as x approached 0. In fact, this one, instead of f, let's give it a different name. Let's call this g. Okay, so the limit of as x approaches 0 of g of x is equal to what? Now, if all we had was sine x over x, we've already did the limit and we got 1, right? Now, I am going to tell you that the limit of this, the limit that I have here is also 1. Okay? Now, you're probably saying, wait a minute. No, that's not possible because at 0, the value is 2. Okay? I did this to emphasize a point. Notice that, remember when we were doing our tables? Okay? And for this one, you might want to go ahead and do a new table, but we had stuff like 0.1, 0.01, 0.001, etc., right? Now, notice that we never plug in 1. We never plug in 0 for x. Okay, so as long as you never plug in 0, you're only allowed to look at what happens as you get close to 0. As you get close to 0, as you go down the second column, it's getting closer to 1. You say, well, but it's not equal to 1 at the destination. Yes, that's my point. We don't care what happens at the destination. The limit only cares what happens as you approach the destination. Okay? So think about that. That's a very important point. Okay. Now, I'm going to finish by giving you the formal definition of a limit, and once again I'm going to warn you that it's going to look weird, and we're not going to do too much with the formal definition, but know that in future calculus classes, if you take more, you'll spend more time and you'll learn all the subtleties of it. Okay? So the precise definition of a limit as x approaches some number a of f of x, let's say that the limit is equal to L, okay? So we want to know, what does that rigorously, precisely mean without any ambiguity? Okay, what it means, and I'm going to give you what's commonly called the epsilon delta definition. Epsilon and delta are just Greek letters. Now, historically, the the two variables that have been used to give the definition of a limit have used the Greek values epsilon and delta. That's the only reason it's called this. Just like slope is traditionally called m, right, and the y-intercept is called b. It's just tradition. So there's no deep meaning or hidden point about the fact that we use these two Greek letters. All right, so don't worry about that. So here we go. For any epsilon greater than 0, the difference between f of x and L is less than epsilon whenever the difference between x and a is less than delta. Okay? Now I told you that it was going to look weird, and but there you have it. There's reasons why we do it this way. It turns out that there's traps that we are avoiding by saying it this way, and it took a long time for people to figure out that this is the way to avoid all the traps. All right? Let me just point out a few things, and you can kind of see some of the reasons people did it this way. Okay? I'll read it and then I'll point it out. So again, for any epsilon greater than 0, so in other words, you can pick any value of epsilon you want. So you pick how close you want the function to get to L. Okay? So the absolute value, the difference between f of x and L, is going to be less than the value you pick. So it's going to be closer than the value you pick, that function is, whenever the x is within a certain distance from a. Okay? Now, notice that, look at what is right after whenever. Okay? So notice this 0 right here. So we don't allow, or we don't, maybe not allow, we don't consider. Okay? We don't consider x equal to a. Remember how I said that we avoid talking about when we're right at the destination? Okay? So this definition avoids the destination. Okay? So notice that. All right? And notice also that the function has to always be less than some maximum distance for all x values within some distance from a. Okay? So think about that. Again, we're not going to emphasize this too much, but now you've seen it for maybe the first time in your life.